So we left off finishing the question 2 on this one. Was there anything that you wanted to have a look at otherwise, or do you want to just continue on with this?
We can just continue with that.
Continuing on? Sure. Here
Yep.
we go. Hey Van, how's it going? Just a quick introduction, just to catch you up on how this all works. So you'll notice there's a couple of different screens. There's one for myself as I am talking. There's also another account in here that is for any handwritten notes that we might do. It's currently aimed at my CAS, so it's probably a good idea to find that account and right click it to pin it. That way you can have very quick access to it. The other thing would be the screen share itself. So if you see at the top of your Zoom window, you'll notice that you've got a screen share there as well, where we're covering any of the particular content. Right now we're going through one of the practice SACs I've put together for Calculus specifically, and I've pulled it from a bunch of different sources. So you might recognize this one if you've looked at the past VCAR exams, but there's more than just that in these. Is that all fair enough? Is there anything I should clarify further regarding that?
At the moment. Do you know I can get the booklet?
Do you know where, sorry?
Yeah, the booklets. Is it just on the?
All of this stuff that we're looking at on the screen share?
Yeah.
Yeah, so those are a add-on to our classes. It's a $70 package that you can buy and grab the whole thing. Whenever we do like our lectures though, I'll typically drop the relevant lectures notes in the chat for free instead. But if you want to get access to this sort of stuff like the practice acts as well, that's I can get you a link for that one specifically afterwards. Okay?
Yeah, all good.
Sweet. So, cracking on with this question 3 sequence here. So, there's a bit of background to it. You can have a read of the background if you like, although most of the key information has been summarized in the image that has been provided to us. If the depth of the liquid in the tank is h meters, so in the diagram we're assuming that the height of the liquid in this conical tank is going to be roughly there, you know, h just being a stand-in for could be any particular height of the liquid. But assuming the depth of the liquid is h, we are now trying to find the radius r, so that's going to be that bit there, of the surface of the liquid in terms of h. So r equals something with h in it. Just for anyone new with us, this is a review class, so there's not much of me doing the lecturing, more so it's more like a workshop sort of thing. So I'll leave it to you guys to have a little think. How might we start going about this one? There's a fair bit of information to digest there, so no rush. This one uses a concept that isn't taught too much. You definitely look at it at some point. It's not something that you learn math methods for the first time though. You learn it a little bit earlier. And it's got to do with there's
Ratios.
Yeah, there you go. You spotted it. How do we use the ratios in this?
So we can look at the 10:4 ratio
Yep,
and basically apply it to the H and R thing.
that's exactly it. Yeah. So the ratio of 10:4, you could do that as a fraction or as a literal ratio with the colon symbol. Either way, probably a bit easier to use the fractions because you do want to make an equation at the end of the day. So we have a look for handwriting bit. If we do it 10:4, would be the same ratio as, in this case, h to r. You can obviously flip the fraction any which way you want, so long as you keep what you're comparing consistent. Now getting r in terms of h is going to be quite trivial. First, simplifying that fraction, and it is h into r in terms of h. Okay, so r is going to now be 2 on 5 h. I got that right way around. Find r in terms of h. 5. Yeah. Oh, actually, something seems a little bit off there. So one of the dimensions that were mentioned doesn't fully match up to the comparison that we're doing there. Ten and 4 does not directly relate to H and R. It's very close, but not exactly. Ten and H is fine. 4 and R is a little bit off. So think about how, if 10 and H are good, what is it about 10 and H that is a bit different to the 4 and R? Think about what dimensions they're covering. Ten is a height, as is H. 4 is a diameter, R is a radius. So the difference between the diameter and the radius is why this one's a touch off. So when we're doing our ratios, we should have instead actually used this. Yeah.
Yeah, that's half.
Yeah, exactly. So half. You're right. Yeah, let's do it. So basically removing each instance of 4 with the 2. That means this would simplify to just 5. And finally you get a fifth of H, or probably a bit simpler, H over 5. So in summary, basically the application of similar triangles in here, or the related ratios. We noticed that we had a net height of 10 and a net diameter of 4 for the entire tank, and we noticed that because this is a cone inscribed inside of that cone, it's going to have the same ratio of dimensions. Now, the height was 1 to 1 because these were both measurements of the height of our cone, but the difference between the diameter and the radius there meant that we had to halve this dimension in order to properly create that ratio of terms. How we created the ratio of terms was simple, just creating literally a fraction. So it didn't matter what order you did it in, whether you did like 10 over 2 or 2 over 10, so long as you also kept the H and R directly related to wherever you place the 10 and the 2. Anything further to clarify there? Final answer, R equals H over 5. If not, feel free to move on to part II. Proving the volume of the tank is given by that. If you guys need a formula sheet, let me grab a screen grab of that, because you will need to have the generic version of the volume of a cylinder. I'll just grab a copy of that in the background and put it in the chat as a screen grab. Okay, that should be posted now. So that's going to give us the generic volume of pi r squared height. So without using any of the terms from the question, V being pi r squared height is a great place to start. One of the things we're going to notice here is the volume in our question only has h in it, whereas we've got an r squared and a h. It's worth also double checking that the h's and the r's actually match up to what they should, which in this case they do. H is the height and r is the radius there. Oh, hang on, I'm using a cylinder. Where's the other one? Where's the cone? Oh, third pi r squared h. Let's fix that. My bad. That's a bit better. So now we can see we're a little bit, maybe not too much closer, still a bit harder to see how that directly is going to translate to pi h cubed over 75. One of the first things I'd advise would be figuring out how we're going to replace the r in this, because we can clearly see in double I there's not supposed to be any r. The last hint I'll give is because it's indented as I and double I, it usually implies, even just any sequence in general in extended response, usually implies that unless anything drastic has changed, the results of your previous answers can be used to help you out to find the new question's answers. Think about what we ended up with AI.
Can we use the ratio that we found for
Yeah,
R?
that's it. We had a final answer of r equals h over 5. That is true, the same thing as in double I, because nothing about the question has actually really changed, right? We haven't changed our diagram, we're still referring to the same thing. So our finding that r is the same thing as h over 5 applies here. B equals a third pi r squared, which is now h over 5 squared. Make sure you use your brackets, right? It's r that's being squared, so whatever r is, the whole thing should be squared. And now from here it shouldn't be too hard to see how that's going to simplify into what we end up with. So it's going to be a third pi h squared over 5 squared, so 25, times another h. 25 and 3 is going to make 75. That's not a 5. This is a 5. So we're going to have the pi and the h squared, and h make the h cubed. Also put in the meters cubed there because we are in fact still working with the extended response question that has units involved. The reason we didn't need units in the previous one is because it was, yeah, it's basically just a ratio there. Meters divided by meters makes it a unitless outcome. Any questions as to how we've done this show that? Like especially that first one, that first question we went through is something you learn maybe like year 10, year 9, and then it's not explicitly mentioned again with the similar ratios. Yeah, let me know. Otherwise, let's move on. This is Tech Active, by the way, so if you guys have your CAS on hand, feel free to use that to help you. Oh, hang on, question. Oh yeah, which part did you want me to re-explain? Sorry, I thought at the end summarized.
Like just quickly summarizing
The both
the method. Yeah. Just
oh,
quickly.
sure, yep. So at the beginning, what we did there was it basically asked us to find the radius r in terms of h, right? So we know we got to do something with this h and r to try and combine them. What we are noticing about the scenario particular is that it is a shape inscribed inside another shape, right? We have cone inside of a cone, and one of the things about a cone inside of a cone is that the ratios of the dimensions should therefore be the same. You know, they won't be the actual same numbers, but they will be, as far as the ratio is concerned, related to each other in that way. And so the reason why we have to consider that at all is because we need to try and figure out how am I going to get r and h into the same equation with each other. I could think maybe like a volume thing, but then I'm going to introduce a v in there as well, and I've got to figure out how am I going to get rid of that. The only other information that we had was dimensions of the overall tank, which is what leads us to start thinking of ways to incorporate the other numerical information in the question, whether you're looking at the dimensions or whether you're looking at the written version of it. Once you've identified the related ratio there, setting up the actual equation is sort of trivial. So you just compare the numerical height with the variable height and the numerical radius with the variable radius. Which way you do that fraction doesn't matter so long as you keep it consistent left to right. Then from there you have your equation. You're just rearranging for r in terms of h. All good with that?
Yep.
Sweet. As for this show that, we now have the result that r is the same thing as h over 5. Show that the volume of the liquid in the tank is that. Well, first up, volume of the shape. First we need to figure out, okay, well, it's a shape, firstly, it is a cone. So we go down and look at our formula sheet correctly this time, and we pick out the right generic volume formula for that shape. In this case, the cone, 1/3 pi r squared h. From there, if we compare our volume equation with the volume equation in the question, we'll notice a few different things. One is the coefficients are different. You got a 75 in there when we had 1/3. And you've got a h cubed where we only have a h. Furthermore, we have an r squared, which this question does not have at all. So the biggest thing I'd be worrying about in these would be figuring out how to get rid of the variables that don't exist in there. We have an r squared, they don't. There's got to be some way of removing the r. Hence, we're going to look at our previous answer, or anything that's related to, that could relate r and h together. Or at least just r and any other thing, maybe it's numbers. In this case we have just r equals h over 5. So we're going to do our best to sub that in and see how we go from there. In this case it is just a one-stop shop, right? You just chuck in your h over 5, and if you have a look at the working out on that, it does just end up simplifying down there. There's no further things to consider beyond that simplification. Is that a bit clearer?
Yep, that makes sense now.
Easy.
Thanks, Chris.
Yeah, no worries. Okay, cool. Next up, we have a tap at the base of the tank. So that was this little bit here. Well, I guess more specifically, right at the very tip of it. Liquid flows out. Depth of h is given by, okay, so basically this equation that we have here is determining the height of the liquid in the tank with respect to time. So, you know, you turn on the tap, this height slowly starts to decrease over time until it'll eventually, obviously, hit 0 at some point. And this is the function that describes that. The height, how high it is from the base, with respect to time, how much time in terms of minutes have elapsed. It is turned on until the tank is empty, and the follow-up question to that is prove the tank is empty when t equals 20. Hypothetically, what do we think is going to happen if we shove in our t equals 20?
Get 0.
Yeah, 0. Why?
Because it's finding the height of the liquid, so obviously if the height's 0, that means there's no liquid in the tank.
Exactly. Height being the height of the liquid. If the height of the liquid is 0, there should be no liquid in there. So let's see if that's what comes out to be the case. I can assure you it will, unless I somehow fat finger the keyboard by accident. 1 over 1600 times bracket x cubed.
Wait, this is tech active, right?
This is tech active, correct.
Ah, okay.
Cool. So yeah, a good rule of thumb for your extended response, you're pretty much always, at any point you get a new function defining that new function, because it becomes easier to then sub in anything that you want to test things or plot things. In this case we can see clearly h of 20 is going to be 0. I do recommend keeping x as the variable rather than t, simply because if you do want to sketch it, t is not going to be considered on the axis, and so making sure that you keep whatever the variable name is as your x-axis, as x specifically. You can call the function h, x, well, anything else that you want to call it, just leave x as the variable of the input. But yeah, that's exactly that. Now I just realized it is a show that, so technically you would be doing the actual arithmetic. But that is just arithmetic at the end of the day. So unless anyone wants to see me do that arithmetic, feel free to move on. Is that a thumbs up for show the arithmetic?
I know, all good.
All good? Okay. Awesome. When t equals 5, find the depth of the liquid in the tank. I guess one thing I should probably highlight here is, I don't think they've ever done it differently, but it is worth pointing out sometimes, maybe, they might say a different unit than they otherwise specified. So always going back to the initial definition of time in terms of minutes, if they said t equals 5 hours, well, one, that's a bit misleading. They might just say 5 hours, making sure we're always keeping the units consistent in here. That was just a random thought that came to mind. I don't think it's ever been an issue, but something worth pointing out. But yeah, CI is going to be a very similar idea, right? When t equals 5, find the depth of the liquid. What are we going to do there? CI, depth of the liquid in the tank when t equals 5.
Isn't that just the height?
Yeah, so they've defined h as depth, right? So depth of liquid as h. So yeah, whether they say depth
So
or
h of 5.
h of 5. Yeah, exactly. H of 5. Give the exact, and don't give the decimal rounded, because it didn't say a number of decimal places. Cool. Next up, maybe a little bit more challenging. The rate at which the volume of the liquid is decreasing. Now, the indentations here are going to matter on how you approach this. The rate at which the volume is decreasing.
So the derivative.
Yeah. Now, derivative of what?
Derivative of h.
Have another read. The rate at which the volume of the liquid is decreasing.
Yeah.
What is that actually referring
Okay. So that's the volume.
to? Yeah, so we got a depth equation here, but they gave us
Yeah.
a volume equation here not long ago. Now that actually I would say is a bit misleading. Usually in the indents, when they indent it again, usually it's sort of self-contained, but in this case they were a bit nasty with it. So paying attention to the specific units or measurements that are actually being used there. But okay, so I didn't actually define the volume one, so let's get that one sorted. We'll go v of x is pi x cubed on 75. But yeah, you were right as far as like using derivative for this. Rate at which something is decreasing or increasing is all going to be, like, any rates of change are going to be derivative related. So derivative of the volume equation is going to be useful for this, absolutely. Once we have our derivative, what are we doing with it?
We find the value at 5.
The value at
X
5?
equals to 5.
Yeah. So let's have a look. So it's going to be t equals 5 is what they wanted, which is why, because it's indented, we're going to use that t equals 5 from the header of the question. But let's just worry about the units again, and sorry, not the units, but the variables. This is a v of h equation. So this is maybe one of the worries about using x consistently in a CAS. Yes, it's helpful for the graphing, but it also helps when you're writing these down, at least on the paper, definitely use the same variables. So because this is a v of h equation, we don't actually really have a spot to sub in that t equals 5, but we do have a spot here. So you could use that. I was thinking maybe you could use the ratio, but that's actually not the case, because that was R and H together. The only thing that has T and H together is going to be the function itself. So we're going to, in order, first up, convert our T value into a H value. So that's going to be, actually we have that already. That's why they got us. Maybe that's another little thing to watch out for there. This being I versus double I. That's maybe another hint that we should be using our previous answer, because we already did our, what is this, H of 5 here. All we're going to do is use that as the substitution, because this is a H function here. So it's going to go into our volume equation here. Let's go Control C. Actually, that's not going to work. Let me grab a copy of that first, and then Control C it. Cool. Now correct to 1 decimal place, so we'll hit our Control Enter. That's going to get us 5.0 meters cubed. Actually, I won't finish that. What's the unit here?
Meters per minute.
Meters per minute. I think it's on. Let's have a look. So volume's a meters cubed thing, and yeah, this unit's going to be tricky actually. It's going to be
cubic meters per minute.
Yeah, I don't even know if it's going to have time in it at all, because it's a the variables that we used was V and H. That's a tricky one. Meters cubed per... What's H? Meters. Meters cubed per meter? That seems off. Let me have a look.
I mean, I've seen units like that, so
Yeah,
I've
it is
seen
a...
centimeters per centimeter square or centimeter cube per centimeter.
Yeah. It's a thing. Units do that sort of thing. No, they did do meters cubed per minute. I guess because it does go back to being time. Yeah, that one's a bit tricky. Because it's a related ratio, I guess, because it all the way had a fundamental based off of the time. Yeah, okay. That one's good to know. So when you have a sort of like cascaded set of functions, you yeah, the units persist through that. Anyway, that's about it for that one then. So in total, there was a few things that were weird there. First, it mentioned volume, right? So we had to then go ahead and use our volume equation to sort that out. From there, we had to diff the volume equation to get it in terms of the rate, because it said the rate at which volume is decreasing. But we noticed that it's a V of H equation, not a V of T equation. So we had to do something to convert the time value that we had into a H value. Once you have that, then the rest is just the substitution at that point. Any questions there? That was a 3 marker there, so it makes sense that we had a fair bit to do.
If this is tech active,
Yep, take active.
then for the questions that had 1 mark, can't you just write out the answer?
Yeah, my markers are just answers. So we'll
Okay.
show that you have to give working, but like
Yeah, because I was
CI
confused about the show that, because
Yeah.
the CAS is kind of just doing that.
Yeah, show that you show working always. If it's just like this, the depth of the liquid, then yeah, just give answer.
Wait, so for the show that, show that one,
Yep.
the 1 markup, would you just have to do it manually?
Yes, unfortunately. But like, as far as doing it manually, like you'll say 10 plus 1 over 1600, 20 cubed minus 1200 times 20, and you'll get your CAS to actually evaluate 20 cubed and 1200 times 20
I
and
see.
write that out.
Yeah.
So you can still, it's CAS aided, but not just final answer. Same
Yep.
thing with this one here, with a show that if you needed the CAS for whatever reason you could. But this one here, you didn't actually need to show any working, but you'd kind of want to anyway. This isn't really something you do on the CAS to get the related ratios. But technically speaking, you could just give final answer here without anything else and be fine.
Yep. But as a general rule, 1 markers for tech active don't really need working out.
Yeah, unless the keywords show that exists,
Yep.
1 marker is just answer. So basically, the real rule is there's always 1 mark for answer. Every other mark in there is going to be for working. So if you've only got a 1 marker, well, it's just going to be answer, unless they specify, give me more working. Okay, we got a fair few more questions here. Let's see, because we got a few students submitted questions as well. I think, how much different is this one going to be? The shelf is placed 2 meters above the vertex from the moment the liquid starts to flow. Find out how long in minutes until h equals 2. Yeah, okay, this is related. I reckon I'll be able to get through this. So let's have a think. Shelf is placed 2 meters above the vertex, so that's going to be that thing there. From the moment the liquid starts to flow from the tank, find out how long until h equals 2. So we want like a h of t equation relating the h to time, and we have that. So I'll pull up that equation specifically on the CAS, our h of t. Yeah, I think that one should be it. Let me just double check. Yep, that was our time equation related to h. This one's a bit of a weird one because they're giving 2 marks for it, but the solution is rather straightforward. At least as far as, sorry, it's like a one-liner. You can do it in 1 line. So perhaps this one would be 1 mark giving the actual equation that you need to solve, and then another mark for the, well, maybe there might be multiple solutions. Maybe that's why we have to get a 2nd mark out of it. Anyway, the equation that I have on the CAS is a h of t equation, h being one of the units that we have, and time being the other thing that we're trying to solve for. We have one of the 2 variables in that equation. What are we going to do to get the other one? As a reminder, depth is taken with respect to the base here. So like this bit here is considered 2, this bit here is considered h. Right, it's not like in the reverse or anything like that. All good. This one's just going to be a CAS solve. Right, so we're told our h is equal to 2. So in other words, our h of t is equal to 2. It says find out how long in minutes it'll take to get to h equals 2. T is already in terms of minutes. So if we just solve for x, and then get our decimal place from it, we'll notice we have a whole bunch of different options here. So we got -39, +12, and whoops, 26. So we got a bunch of different possibilities there. What do we think is the likely answer that we're looking for here? Only one of them makes the most sense, even though the function tells us there's 3 solutions. Remember, this is a real-world scenario, in quotes. Or maybe rather than finding what would be the most valid one, let's think about ones that are nonsensical. Which of these, negative 39, positive 12, and positive 26, which of those seem nonsensical for time? Remember, these are all time in terms of minutes. So negative 39 minutes, 12 minutes, or 26 minutes.
Time is positive.
Yeah, time's only going to be positive. Time t equals 0 is usually, in every scenario, going to be the first moment of that scenario. So you can already ignore the negative one. The more tricky one is going to be while we have two positive solutions. Time is allowed to be positive, and they're both positive. The wording of the initial scenario here is going to be helpful. T minutes is the length of time after the tap is turned on until the tank is empty. That sentence there helps us determine which of these is actually valid, the 12 or the 26. Which one would it be and why?
Is 12 correct?
12 is correct, yeah. Why is that correct?
Because the tank is empty at t equals 20.
Yeah. Well, the tank is empty at t equals 20, absolutely. And because the tank is empty at t equals 20, well, 26, it's no longer running anymore. Now, this is a polynomial, it's a model, I'm trying to model the height, and as such, usually what you find is they're only defined over very specific domains, outside of which they become invalid. That's what we do pretty much every time we have polynomials, right? We start by getting the equation that we're trying to use, or maximize, minimize, whatever it is, and then we cut it off at the spots where it's valid. Okay, let's have a think. As soon as tank is empty, the tap turns itself off and becomes poisonous. It flows into the tank at a rate of 0.2 meters cubed per minute. So there's our ratio there. How long in minutes after the tank? Oh, it flows into the tank. Gotcha. How long until it becomes a depth of 2 meters again? So there's our meters cubed per minute. This one's going to be tricky, I think. So there's that unit again, the 0.2 meters cubed per minute. We knew what that was relevant to before. That was relevant to the ratio that we have. Granted, this one's a different number, but the unit still persists. What did we have last time? So we had, in the most recent version of that question, we had to figure out the rate at which volume is decreasing based on t equals 5. In this case, we're not given a time value to start with, but the rate itself. So the hint would be that we're essentially doing the reverse of this. right? We wanted to find the rate based on the time. In this case, we're given the rate and trying to find the time. In fact, is the depth the same as well? Not quite. Depth is a little bit different. But it's effectively going to be the reverse. So you come off me, but nothing came through. Could you repeat that? If you intended to.
My bad. So good.
Nah, all good. It's going to be a tricky one. I'll say this was a pass VCAR one. 11% pass rates on these. Okay, let's have a think then. So basically, the 0.2 is going to be our dv, right? The derivative. That's what we had before. So the derivative of the volume, now we need it specifically with respect to time here, dv on dt. Now dv on dt is related to the dv on dh that we created, but because we needed to get it in terms of time, we needed a related thing. Now we did a substitution approach. There is another way you can go about this as well. So rather than just replacing the time with the equivalent h, you can also set up what's basically a chain rule, dh dt. So what you'll notice is when those cross out, you get dv dt equals dv dt rather, sorry. This is something we can calculate because we have a volume with respect to height equation. This is also something we can calculate. We have a height with respect to time equation. dv dt, we're told, is equal to 0.2. So essentially we calculate this, calculate that, multiply them up, and what you end up with is going to be 0.2, from which then you solve for the t in the equation. That's the gist of it there. So if I copy down what we had for each of those, in fact let's just do it from the beginning. So v, so it's going to be pi h squared on 25, pi h squared on 25, and then our dh dt I don't think we actually ended up getting because we're doing a slightly different approach to it. dh is going to be 3, so this is in terms of time, this one, so 3t squared on 1600 minus 3/4. That equals 0.2. 0.2. We got a h, we got a t in there, but we do have h in terms of t already. Where was it? I guess I didn't write it down. It was just the height equation that we had. So h in terms of t already is that. Sorry, that's blurry. That's better. So this is h of t. So all you're doing is replacing the instance of h with what t actually, with the thing that has t in it. That gives you an equation with only t, and so that should be solvable from there. So let's have a look. 331, so it's going to be dv dh. So you got to replace this with that one, multiplied by dh dt, which is that, equals 0.2, and unless I've done a substitution error, we're going to get our only valid solution of time. Now this one is allowed to go over 20 minutes because this is post the question that we had before, right? Tank is empty at t equals 20, yes, but it's now being filled up with the poison afterwards. So in fact, the fact that we got an answer after t equals 20 actually only serves to more validate our final answer for this, because we expect it should be afterwards. Now let me just double check. This one you actually needed exact, so let's grab that specifically. Uh-oh. How are we going to get exact? That's a bit of a shocker. This is the right equation, equals 0.2. No exact. That one I'm a little stumped by. I don't know why that didn't come out as exact. That is the way you're supposed to do it. Uh-oh. Yeah, I'll have to look into that a bit more. I notice we are running a bit out of time. We have some student submitted questions to do. But before I guess I move on, as far as the approach there, we did a little bit of a different thing, getting a sort of a chamber looking thing. Does anything about the concept there need to be clarified? I know we didn't get our exact answer, and I'm not sure why the CAS is breaking a little bit there, but if I find out, I'll follow that up. I'm more interested if you guys are getting the concept as to why that's the way to go about it. Any questions about that at all? Cool. Okay. Now, as far as... oh my god, I just closed it like a stupid. It's fine, I got the worked answers to them. So the questions that we had submitted were regarding the exponentials and logarithms chapters. The good news about this one is, because so many of you are having trouble with it, I actually went ahead and wrote work solutions to all of them. So that's why I sort of waited until quite a while, because they're already written down. All I gotta do is read them off. So let's have a look at the ones that were specified. These are on the modules as well, by the way, relevant to the it's going to be in the functions relations section with the exponentials logarithms. So let's have a look. 13a, question 11b. Okay, 11b. Let me just close up all this. Hang on, what? 13a, unit 1 and 2, 11b. Did I just not do this one? Surely not. Uh-oh, let me double check. A. Wow, I just didn't do them. That's crazy. Alright, let's do it then. That is the right one. 11b, sorry. Okay. So, 11b. Simplify all of these, give it in terms of positive index form. So what I'll do is I'll pull up a similar sort of idea just so you can see the kinds of things that I would be considering, and then we'll go in and do the actual thing itself. This will probably be one of the closest ones here. So let's have a look. From here, simplifying a similar looking thing, one of the first things I'm looking to do is to pretty much simplify any other brackets that are involved. If they have those cascaded powers, then one of my first point of calls is going to be to do those cascaded powers using the index law to distribute the cube into all of these individually. So in this example we would do that here first. Right, you've got that bracketed term there. So let me write that one down just so we can all be on the same page. That's a big one. So x cubed y z minus 2 times 2 x cubed, maybe I'll get rid of this other bracket, 2x cubed y minus 2z all squared, and then xyz negative 1, xyz negative 1. So, as I said before, all the other stuff is going to maintain the same, but we're just going to distribute those powers through. X cubed y z minus 2, 2 bracket, now it's multiplicative, so x6 y negative 4 z squared. X, y, z minus 1. Okay, from there, again, the next thing that I'm looking to do is if there's any like division symbols, I want to convert those into a multiplication symbol instead, just because I personally find it easier to think about how things simplify via multiplication rather than division. You don't have to do that, that's just a personal preference of mine. In this case we have no division symbols. I don't consider the fraction as a division symbol because for whatever reason, it's probably a bit easier to see how things simplify across the fractions rather than via the actual division symbol. If you do have multiple fractions, multiply them together. In this case we have one big fraction, so we don't have to worry about that. All we're going to do from here is simplify anything that we already can see across the numerator and denominator, and then finally flip things back to their right spots. So that's pretty much the order in which I'm considering these things. So coefficient, we'll bring that out the front. We've got an x cubed and an x6, those are going to add together. Remember, multiplying across means the indexes add. So x9, we've got a y here and a y minus 4 here for a total of y minus 3. Z negative 2, z squared, those are just going to cancel out for z0. And that's it for the top. X's, y's, z's, and the 2. Yep. X, y, z minus 1. Then from there, you don't have to flip negatives to positives, but I tend to, just so it's easier to see in my mind what is actually happening. So we're going to have x9, and this y cubed is going to go down on the bottom. So y cubed on the bottom, adding to that is going to be y4, and this z is going to come up top. From there, anything further to simplify, I'll then tidy up from there. 2, so x9 and x is x8. You still got the z, and then the y4. So in summary, one of the first things I'm doing is looking for any brackets with indexes on them and just shoving that all the way through. The next thing I'm doing, at least in this circumstance, because there's no more additional fractions or division symbols between other fractions, I'm moving straight on to just looking at numerator individually and denominator individually. From there, once I've simplified all that, I personally will just shove the negative indexes into the positive, into where they are equivalently positive, and then simplify from there. But again, you don't have to do that. You can use the rule that it is this index minus this one for y minus 4, and then only then shove it at the end. But working with positive numbers tends to be the best for most people. How's the process there? Anything about that need clarification? This is just my way of doing things that I find keeps things repeatable and consistent. Any questions there? If not, let's hope that I did 13b. So 13b, 3e. Cool. Okay, so for this one, let's have a look at the actual thing that it was asking. Double check, 3e. Okay, so 3e. The whole sequence here is there's a bunch of roots involved, and it makes sense this was the first one that was a bit weird because all these are multiplicative, and then suddenly they throw a plus in the way just to make life harder. What are we doing there? Well, I'm assuming I just combined the fractions to start with. Is that what I did? Yeah, sure is. So first thing I did there was actually just combining the fractions. This one's all written in the screen share, so we'll have that as the main point of reference for that one. To get them as same denominator, well, look at the denominator of the first one and multiply top and bottom by that root. What we'll find is that not only will it give the same denominator, but it'll also end up cancelling the root on one of those terms because you're multiplying by the square root of itself. This is root a times root a, which is why you just get back to a. From there, they are the same denominator, so you can combine them now, and all that's going to happen from there is the constants are going to disappear, going to condense into each other. How's that one there? The main idea there was making sure you get everything as the it's an addition of fractions, so you got to get the denominators the same. Are we cool with that one? Okay, 13E had a bunch, so question 7. Oh, went too far. Question 7. Yeah, okay, that's a monster. Okay. So this is where we're making use of, I believe, no, this is actually going to be all fully log laws, huh? Interesting. Okay, so it's given us a couple of logarithms that are equal to different constants. Log 10x is a, log 10y is c. We got another log 10, which has a bunch of x and y's in it, and we want to get rid of those x and y's and turn them basically into a's and c's. So what do we do there? Let's see, what did I start with? There's a couple of ways you can do this. For instance, you can convert these to exponential form, and by doing so you can essentially get the x and y's on their own and then shove those in there. It looks like I did a little bit of a different thing by first, yeah, I did. So rather than converting these to exponential form, which you can do, instead, just to show you a little bit of a different thing, you can actually split up this big nasty logarithm using the product and quotient laws. Right, quotient law meaning you do your subtraction of that thing, and the product law meaning that you do the additions between those all. So it's 100 multiplied by, so plus x cubed, multiplied by y to the power of minus half, again plus, and divided by y squared. So finally a minus at the end. Then from there, all we're doing is simplifying this side now. So log 10 of 100 is a known value, that's just going to be 2. Log 10 x cubed, we can take the power out of that. Again, the power of minus a half, we can take out of that, and the power of 2, again, taking out of that. That's just using the power law. From there, what we're going to notice is we have a thing that is log 10x is a. Here's log 10x. So if log 10x is a, replace log 10x with a. Same thing here. Log 10y is c, so replace that log 10y with c. Same thing with this one over here. That's also a log 10y. And then yeah, that finally gets you in terms of a and c. That's one way of doing it. Any thoughts or questions there? The other approach would be flip. I'll do this briefly. So we had the expression which was, I'm just going to do one of them, log 10x is a. So you could flip this to the exponential form. 10 to the power of a is x. Now that you have x as its own thing in terms of a, you can go ahead and look at that big nasty log 10 bracket 100 x cubed and so on, and just replace that x with this. You can do that, perfectly fine, but I'll just show you a different way on there. Cool. Alright, that's it time. I'm going to keep going with the other questions just because there are a few, but I've got them all written down, so it shouldn't be too much longer to continue. So if you guys do have time, feel free to stick around. More than happy to keep going with it. But if not, I'm glad that you came, and I appreciate it. I'll see you next time for those who have to leave.
Thanks, Chris.
No worries. Yeah, no worries. Okay, next one up was 10e. Okay, what are we actually doing here? What does it say? Oh, this is all the way on 13e. Solve for x. Okay, so you got a bunch of logarithms and you're trying to solve for x. One of the first things we're trying to do in these circumstances is condense everything down into one logarithm. That way it's a lot nicer to work with. And we're going to use our log laws to achieve that. A good starting point is going to be power law. If you have any coefficients on your logarithms, then it kind of makes it hard to use the other log laws. So that's the first thing I'm going to do. Chuck that 2 in as a power of that 5. From there, what are we going to do? Well, I'm noticing an addition of 2 logarithms, so we can combine those using the product law. 5 squared times x plus 1. I've also taken it a step further to also just subtract this one over. And because it's a subtraction, quotient law, right? This thing divided by this thing. All said and done, we now have logarithm equals constant. From here, we'll just convert to exponential. So solving logarithms is always a 2-step thing, essentially. Combine them all down into one logarithm, and then convert to exponential to finish the job. Same thing if you have exponentials, actually. Combine all the exponentials together, and then it's usually a bit harder to combine the exponentials together, but if you can, you should do it. Anyway, converting to logarithm, so 10 power of 1 equals bracket, and this is now just basically linear at this point. Solve for x. Happy with that one? Sweet. And finally f, which I imagine will be the same idea. Let me just have a look. Yeah, exact same idea here. EF. Were you doing A, B, C, D before? Or did it just start getting hard at E and F? I'm trying to see the differences here. Only differences I can see is that there's 3 logs as opposed to 2. Because D and B both had a constant in there as well. This one appears to be basically the same thing again. But anyway, so it's going to be the same idea, right? Looking for any coefficients. Oh, t to the left side, okay. So it definitely, so it was the fact that it was the constant that was the issue maybe? So this one, yeah, this was just log equals log, log equals log. Hell, for that one you could have even just made the brackets. Oh, not quite. Actually, this is 2. Yeah, all these are log equals log, so was it this thing that was the issue? The constant? Yeah, okay. Well, I'll show you another work solution again, just so you can see that it's a pretty repeatable thing. First up, any coefficients that we can see, knock them off. So power of 2 on the bracket there. From there, there's an addition here, so it's going to be a product law. Expand that all the way up. Oh, and simplify. Then from there, just getting all logarithms on the same side, so subtracting this one over to here so that I can then do my quotient law. From there, I have 1 log equals a constant, so I now flip it to an equivalent exponential. This is not quite linear. Oh, well, it does end up being linear because the x squareds end up cancelling out. But yeah, just multiply the denominator across, expand it out, expand, 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 simplify, simplify, simplify. So yeah, you see the approach for them is similar. Start with power law, then do your other product and quotient laws, and then finally when it's all combined together, do your exponential. I think that's all the ones you had. Yeah, ending at F. That's all of them, yeah? Got confused. Answer sheet said... Yeah, oh, there's different... Okay, so if the answer sheet's telling you one thing versus another, the reason why is because this is algebra, essentially, and so there's a bunch of different ways you can do it. So you can, what they've done there, I think, is convert the constant. Because log 1010, this constant of 1, anytime you have log of base and bracket the same, log AA, that always equals 1. It is a way you can do it. I actually did have a set of solutions that did do that, but I thought it's a bit confusing. And so I was like, screw it, just do it this way instead. You're allowed to have a constant in this, so long as you then go to exponential form afterwards. So that's what they're getting at there. Any constant 1 can be converted into log 1010 if it's constant, or log base bracket, whatever you want. These are all log 10s, so you want to keep it as 10. If you had like a 2 there, for instance, you could do 2 log 1010, because it's 2 times 1. That's what they're doing there. Does that explain why they've got log 1010s going on? Yeah, okay. So doable, but yeah, it's still fine. As long as you understand the methodology there. Cool, alright. That's about it then. Any further questions? If not, I'll let you guys enjoy the rest of your day. Sweet, thank you.
Thanks. Have a good weekend.
Yeah. So you had a few tech issues.
Yeah.
Yeah. Is it so? Your screen being blank. Did that end up fixing itself?
It's just an internet problem.
Oh, it's an internet issue. Okay. Cool. So was it the whole thing went black, as in your literal monitor went black, or just like different screens on it?
Everything was just stuck, and then I switched windows, and yeah, everything just went blank for some time.
Nice.
Yeah, and that happened quite a few times during the meeting, so I had to
Shit.
rejoin multiple times.
Yeah. Okay. I noticed you rejoined once, from I think from phone to computer, but I can't see the other
Yeah.
ones. Damn. Well, the recording will go live on this. It'll be a lot more obvious once you can see it. So if there was anything that you needed more clarification regarding, then those will be there, I suppose. Those will go live by.
It's fine. I think I got all of it.
Oh, okay, cool, easy. Well, hopefully, things are better for the next time.
Yeah, hopefully.
Oh, I'm actually seeing a note now.
Yeah,
My
so-
internet connection's unstable. Holy shit! That's perfect timing. Good thing we're ending it. All right, I'll let you enjoy. Take care.
Okay.
Bye.
Yeah, see ya. Have a good day.
You too.
Have a good weekend.
You as well.